Hello everybody. I am going to go through the questions I just asked you to do. First of all, so if you have done those questions, please make sure that you mark them as we go through. Some of them seem to have come up already. So number one, write the length 500 meters in different units. So you may have decided to do it in kilometers, which is 0.5. You may have decided to do it in centimeters, 50,000 centimeters, or you might have decided to do it in millimeters, which is the example that I suggested, 500,000 millimeters. You can see the next ones are already there. Kilo means 1,000, therefore kilogram means 1,000 grams. What is milli and centi? Milli is 1,000th, so a millimeter means 1,000th of a meter. Centi is 100th, so a centiliter is 100th of a litre. And then for the second question, parts A to F, I asked you to do standard form. So I gave you this example. I'm hoping that you have managed to do these because you've learnt this with Mr. Morkison. I'm assured that you've done this before. So I'm just going to put the answers up for you. I'm not going to go through how to do this. However, if you are struggling with this, then drop me an email and I'll try and help you. Okay, so we've got 4.36 times 10 to the 5. 0.005 goes to 5 times 10 to the minus 3 because it is a small number. We've got a negative power there. The next one, 6.57 times 10 to the minus 6. 35 goes to 3.5 times 10 to the 7. And last one, 2.75 times 10 to the minus 10. Okay, so probably a little bit more tricky for these ones where you're actually already in standard form. Now, one thing about standard form, which I'm sure you know, is that you can only have one number before the decimal point. So this is not in standard form. This is because there's one single unit before the decimal point. So you can't have, if you put decimals in here, it'd be 35.0. That's not in standard form. I think you probably know that already, but just as a little side note, this is technically not standard form. These ones are, because you can see one number and then the decimal point. Right, okay, so what we're going to look at today is distances in space and how they can get very, very big. So now I want to introduce you to the word prefix, which you're already kind of familiar with, and I've said here possibly without realizing it. So when I say prefix, what I mean is the bit that goes before the unit. So milli would be a prefix to millimeter, kilo, the ones we were just talking about, centi, those are all prefixes to the unit itself, which is the meter or litre, whatever it is. So a kilometre is meters with a prefix of kilo. Okay. Now, what you don't know, and I have checked this with Mr. Morkison as well, is that you can kind of convert between standard form and prefixes. Okay, so here's an example at the bottom. So 1,000 meters. We know in standard form that is 1 times 10 to the 3, because we have moved our 0.1 to 3 times, so we need times 10 to the 3, and we can imagine 1.0, we've put it there, so it's gone into that point there. Okay, so that is how we write it in standard form, but you'll probably also know that 1,000 meters is 1 kilometer. So therefore, if you see a number, something times 10 to the 3, this number here, you could also say it is in kilometers in this case, okay? Or litres or whatever it is. So these are all equivalent, 1,000 meters or 1 times 10 to the 3 meters or 1 kilometer, okay? They are all equivalent. So the standard unit prefix for 1,000, 10 to the 3, is kilo, okay? So if you see this, if you want to, you can get rid of times 10 to the 3 and just put kilometers instead of having this 10 times 10 to the 3. Okay, so that's what I mean when I'm talking about a prefix. I'm talking about this little k there, the kilo, and there are lots of them. Okay, so let's have a look. Here we've got 0.001 grams. I'll read this to you because it's quite a lot of writing. So I've already said this. As many measurements such as length can be extremely large or extremely small, writing the numbers down becomes tricky, and this is really relevant when we get to space stuff. This is why we have standard form, which we have covered recently, or you have covered in maths. However, we also use prefixes instead of standard form, okay? So here is the example, 0.001 grams. If we write it in standard form, we get 1 times 10 to the minus 3 grams. Or if we write it with a prefix, we get milligrams, okay? So the standard times 10 to the minus 3 is milli. Okay, now if I go on to the next slide, there's a huge load of prefixes, and we can see how they kind of go between standard form, the actual number itself, and the prefixes. Now there's no reason you need to learn all of these, but it is worth having a look at them. So you can see down this left column, these are the prefixes. Okay, so we've got pico, nano, micro, milli, centi, deci. Now, these are all small ones. We've met micrometers before. We talked about micrometers when we're talking about cells. Nanometers we might use for cells as well. And then when we're getting into particles, we're talking pico, or even smaller numbers than that. Then if we go to our standard number one, nothing. It just would be meters or litres or whatever. And then we've got deca. Now, we don't tend to use deca very often. Hecto. Again, we don't tend to use hecto. Kilo, we're familiar with. And then the big ones, mega, giga, and tera. Okay. So these are our prefixes. These are the things that we can put before, let's just stick with meters. So before meters or whatever your unit is. So picometers, nanometers, micrometers, millimeters, centimeters, decimeters. Meters would be here where there isn't one. Decameters, hectometers, kilometers, megameters, giga or gigameters, and terameters. Okay. So the only ones really that you kind of need to know, even for when you go higher up the school, is kind of nano, micro, milli, and then kilo, mega, giga. You don't really need to know tera. You might do if you're going on to do A-level physics or something, but not too important really. The point is that you can use these, or you can use your standard form, as you can see over here. Now, this would be the actual number. So let's imagine if we're changing numbers. So 1 is our middle point, and we're going up 10, 100, 1,000. So 1 times 10 is 10. 10 times 10 is 100. And 10 times 100 is 1,000, etc. So you're timesing by 10 each time. So this is what the decimals would look like. So if we are dividing by 10 each time, go all the way to here, we're going to have loads of zeros. And these numbers become very, very tricky to work with because it's very easy to miss a zero. You don't want to have 0.00000000000 and then have the numbers that you're dealing with. Okay, so it's much easier to then write that as 1 times 10 to the minus 12. Okay, and you should be able to convert between these already. The only extra thing really that I'm adding to what you've already done with Mr. Morkison is this idea that you can, if you want to, instead of writing 1 times 10 to the minus 12 meters, you could write 1 picometer, 1 pm, okay? Or another example, instead of writing 1,000 meters, you can either write 1 times 10 to the 3 meters, or you can write 1 kilometer, put the prefix label there. Okay, now also a reminder, this stuff at the bottom, if you've got a positive power large, the larger that is, the bigger the number. So this is 4.3 times 10 to the 6. I don't know why that's come up. I can't get rid of it now. then we could write it like this. And then if you've got a negative power, then you're going to get very, very small numbers. Okay, these numbers are actually much easier to work with than these, especially when we get to loads and loads of zeros, either after the number or before it. Okay, so it's just really worth noting, because we're going to be talking a bit about big numbers. The main point is, once you get to space terms, you're going to be looking at numbers which have, hundreds potentially of zeros on the end. And it's much easier to talk about those in standard form, so 1 times 10 to the 52, rather than have 1 with 52 zeros on the end. Okay, right, let's leave that for the time being and talk specifically about space now. We're not. We're going to talk about maps and scale very briefly. So here is a map of Oxford. I'm sure you're familiar with a map. I think you've probably looked at maps in geography. Okay, and we see where we are. This is central Oxford, isn't it? And on maps you have a key that can tell you what you're looking at, but that's not really the point of what I want to make now. The idea that what we're thinking about is that you have to represent things that are bigger, the actual city, onto, in this case, a PowerPoint slide or a piece of paper. So you have to know something about scale. Okay, so walking maps, which you might use if you go hiking, are often at a scale of 1 to 25,000. Okay, what that means is 1 centimetre on your map actually is 25,000 centimetres in real life. Okay, in other words, the map represents the Earth scaled down by a factor of 25,000. So we've made the map 25,000 times smaller than real life. And that is called a ratio. Now, I don't know whether you've done ratios or not with Miss Morgan, and I'm not going to labour about ratios. There is an extension question at the end of today's work, which you can have a go at if you're interested in working in ratios. But the idea is really that I'm trying to make is that when we're talking about distances in the universe, we are using a really, really, really high ratio. Okay, so on our picture of the universe, we might use a centimetre, and it wouldn't be 25,000 centimetres it's representing. It might be something insane, hundreds of thousands of centimetres, millions of centimetres that it's actually representing. So the universe is so vast that the ratio, if we're trying to draw it on paper, like you've seen pictures of the solar system, the distances in the solar system are very, very, very big. So to draw a picture of the solar system, the scale, the ratio that you use, you're using huge numbers, and you're scaling them right down to paper size. So the ratio is very, 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 very big. Okay, when you do that. Right. So just a note on maps again, and kind of links into the universe. If you are drawing a map, you really need to use an appropriate scale. So if you're looking at drawing a street, you'd probably draw the street, you'd know the real length of the street in meters, and then you draw it in centimeters, or you might draw it in millimeters. If you've got a big area, you're probably going to measure your area of the city, for example, in kilometers. If you're drawing the entire UK, your scale is going to be 1 centimeter to represent hundreds of kilometers. And for the Earth circumference, the distance all the way around the Earth, that's 40,000 kilometers. And you can see that's just the Earth. As we start to get towards space, these numbers get huge. And so we can't really start to represent distances in kilometers anymore, because our numbers just get too difficult to work with. So there is an answer. Okay, and this is where we meet the astronomical unit. So the solar system would go, if we were to measure it in kilometers, it goes from like millions of kilometers to thousands of millions of kilometers, and the numbers get really, really big. Yes, we could put them in standard form, but even then we'd be looking at big powers. So to make that a bit easier, when we're measuring within the solar system, we use something called the astronomical unit. Okay, now the astronomical unit, you can see it written here, or we use capital AU. So what that is one lot of the average distance of the Earth to the Sun. Now, obviously, Earth is orbiting the sun, it's not always exactly the same distance. So they take an average distance, and we're taking that to be 150 million kilometers. That is on average the distance that we are from the sun. Okay, so 1 AU is equal to 150 million kilometers. Okay, and then we can start to use much more easy numbers to represent the solar system. So Neptune is 30 AUs, astronomical units, from the sun. Okay, now we could work out, and in fact you are going to work out in a minute, how many kilometers that is. But again, we're dealing with really, really big numbers. So the idea of using an astronomical unit is really to make measurement easier within the solar system. So here's some examples. We've got planets and a dwarf planet in our solar system. Then we've got how many astronomical units these planets are from the sun. Okay, so as we know, we are 1 astronomical unit from the sun, because that's what an astronomical unit is. It's the distance between us and the sun on average. And you can see the closer planets are closer than that, so 0.4 astronomical units, 0.7 for Venus, and then the further ones, the planets that are further out than us, have bigger astronomical units. Okay, so what this essentially is saying is that Pluto is 40 times the distance from the Earth to the sun away from the sun. Okay, we're 1 times the distance, 150 million kilometers. So to work out how many kilometers Pluto is away from the sun, we would need to do 40 times by 150 million, and then we'd end up with how many kilometers Pluto is away. And remember, these distances we're talking here, we're talking close things in the solar system, in the universe. Our solar system is so close to us, our sun is so close to us compared to other things. Okay, so even with astronomical units, we're getting quite big, and we're just within our solar system. So I'd like you to pause the video and see if you can have a go at these 3 questions. Once you've done them, unpause and we'll go through them. Okay, so hopefully you've had a go at these questions. So let's go through them. First one, if 1 astronomical unit, or AU, is 150 million kilometers, and Neptune is 30 AUs from the sun, how far is it in meters? Okay, now a bit of a trick one, because remember, if we're working out, it will come out in kilometers, and then we have to convert. So first thing to do here is do how many kilometers is Neptune away from the sun. So it's 30 astronomical units. We know that each astronomical unit is 150 million, so we times those 2 together, and we get this huge number, 4,500 million kilometers. And then we wanted the answer in meters, so we've got to actually times by 1,000 again, because we want to know meters, not kilometers. So there's your answer. I'm not even going to attempt to say that number. So check your number of zeros when you're checking your work. Then number 2, Mercury is 0.39 AUs from the sun. How far is this in kilometers? A bit simpler. So we know that 1 AU is 150 million kilometers. We've got 0.39 of them, so we've got less than 1. We times those together and we get, 58,500,000 kilometers. Okay, that's how far away Mercury is from the sun. Whoops. Lastly then, Mars is 285 million kilometers from the sun. How far is this in AU? So what we need to do, we take how far it is in kilometers from the sun, we divide by 1 AU in kilometers, and that should give us how many AUs. So 285 million divided by 150 million equals 1.9 AUs. Okay, so it depends which way you're going as to whether you're working out. If you're working out AUs into kilometers, we need to times by our standard AU in kilometers. If we want to know how many kilometers, how many AUs that is, then we need to divide by our standard AU kilometer amount, which is 150 million. Okay, so just be careful with that bit because you're going to be doing that later in your work. So really make sure you understand when to divide and when to times. So again, you could pause the video and really make sure you understand how these questions have been done. Maybe make a few notes because that is going to be helpful to you when you get onto the work in a minute. Okay, so as you can see, actually, once you're outside of the solar system, even if we were measuring things in AUs, we'd still end up with huge numbers. Okay, so I'm sure you've heard this term and you did some work which was on Seneca on this as well. So for big distances we use something called the light year. Now here's an example. So the Earth to Sirius. Now Sirius is a near star. It's actually the brightest star in the sky. Okay, and the word comes from a Greek word which means kind of glowing or scorching. So if you look at the sky at night, you will see a really, really bright star. Here it is, look, Sirius. It is 8.6 light years away from us. Okay, now I'm going to go into what light years means. You might notice some of these other things. The Pleiades is a constellation people often know. Often people can recognize Orion's belt as well in the night sky. So if you're looking at Orion's belt, go left, look for a really bright star. That is Sirius, 8.6 light years away. It's not our closest star, but it is one of the closest stars to us. Right, so the really key thing about light years is to remember that this is a measurement of distance. Even though the word year is measurement of time. What a light year is the distance that light will travel in 1 year. Okay, now light travels very, 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 very fast. Okay, so if you look at this is how far in kilometers light would travel in 1 year. Okay, so 9.4607 times 10 to the 12, or if you write that out with all the zeros in, that's how many kilometers light would travel in 1 year. Now that is a very, very, very long way. Okay, now to give you a kind of an idea of size, I've linked in the solar system scale of the universe thing that we looked at with cells for you to have a play with later. But also, just to put this in context, the light from the sun takes 8 minutes to reach us. 8 minutes. So the light shines in the sun, takes 8 minutes for the light to travel from the surface of the sun to the surface of the earth. Okay, that's 8 minutes. And the sun is quite far away from us, 150 million kilometers. Okay, this is not how far light travels in 8 minutes. This is how far light travels in an entire year. Okay, so it's a really, really, really long way. But in the universe, this is very short distance. Okay, so they're almost impossibly large to imagine the sizes in the universe. So the large Magellanic cloud in the galaxy is 163,000 light years away. Okay, that's the distance that light would travel in 163,000 years. So if we go back, we times this by 163,000 to get how many kilometers that is. Okay, it's our third closest galaxy. Not only that, it's 14,000 light years across. So if we were to measure it from one side to the other, it would take light 14,000 years to travel from one side to the other. Remember, it takes 8 minutes for light to travel from the sun to us. So this should give you an idea of just how big we're talking. And we're talking close still in the universe. Okay, now I'm going to leave it there, but just as kind of reference point, and I really would suggest having a proper look at the scale of the universe in your own time later on. There are 100 billion galaxies in the universe that we know of. Okay, this is our third closest of 100 billion at 163,000 light years away. Okay, so Sirius, the bright star in the sky, 8.6 light years, I think it was. That means that the light, when you look at Sirius in the sky, you're looking at it as it was 8.6 years ago. If we look at this galaxy through a telescope, we are looking at it as it was 163,000 years ago, because it's taken the light that long to get to us from that galaxy. What that means is that essentially lots of things might have happened in that galaxy. Like some of the stars might have died, some of them might have exploded in something called a supernova, but we don't know that that's the case because we can't see it yet. Okay, so I hope that gives you a bit of an insight into the sizes in space. There's some questions for you to have a go at. Some of them are a little bit trickier than others. And then, as I said, I've also linked in the scale of the universe for you. Enjoy.